Certainly. Here's a script for a YouTube video explaining the applications of integral calculus. Introduction. Opening shot of a mathematical integral symbol. Welcome to your channel name. In today's video, we're going to explore the fascinating world of integral calculus and its practical applications. Integral calculus is more than just a mathematical concept. It's a powerful tool used in a wide range of fields to solve real-world problems. Whether you're a student delving into calculus or someone curious about the practical uses of integrals, this video is for you. Let's dive into the applications of integral calculus. 1. Calculating area and volume. Visual illustrations of calculating area and volume. One of the most straightforward applications of integration is calculating area and volume. By integrating functions that describe shapes, we can find the area under curves and the volume of irregular objects, revolutionized around an axis. 2. Finding center of mass and moments. Visual diagrams showing center of mass and moments. Integral calculus is used to determine the center of mass of objects with varying densities and to calculate moments, which are essential for engineering and physics applications, like balancing structures or designing bridges. 3. Physics calculating work and energy. Visual demonstrations of work and energy calculations. In physics, integrals help calculate work done by a force, which is vital in mechanics. Integration also plays a role in finding potential and kinetic energy, aiding in understanding the energy transformations in various physical systems. 4. Economics, analyzing supply and demand. Visual graphs illustrating supply and demand curves. Economics relies on integral calculus to analyze supply and demand curves. Integrals help calculate total revenue, consumer and producer surplus, and can even model complex economic scenarios. 5. Engineering solving differential equations. Visual examples of differential equations in engineering. Engineers often encounter differential equations in their work. Integrating these equations is essential for solving problems related to heat transfer, fluid dynamics, and electrical circuits, to name a few. 6. Biology modeling population growth. Visual graphs showing population growth models. In biology, integral calculus helps model population growth and decay. By integrating differential equations, biologists can predict how populations will change over time, aiding in conservation efforts and disease control. 7. Finance calculating compound interest. Visual calculations of compound interest. In the world of finance, integrals come into play when calculating compound interest. They help determine the future value of investments, loans, and savings accounts, which is crucial for financial planning. 8. Computer graphics. Rendering 3D models. Visual examples of 3D modeling and rendering. Computer graphics rely heavily on integral calculus for rendering 3D models and generating realistic images and animations. Integrals are used to calculate shading, reflections, and lighting effects in computer-generated imagery. Conclusion. Visual host summarizing key points. In conclusion, integral calculus is a versatile tool with a wide range of applications across various fields. It helps us solve problems related to area, volume, physics, economics, engineering, biology, finance, and even computer graphics. Understanding the power of integrals opens the door to solving complex real-world challenges. Closing shot of a mathematical integral symbol. If you found this video informative and want to see more math-related content, please give it a thumbs up and consider subscribing to our channel. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and remember, the applications of integral calculus are endless. Introduction. Opening shot of a mathematical integral symbol. Welcome to your channel name. In this video, we're going to explore a range of integration techniques that will help you tackle more complex integrals with confidence. Whether you're a calculus student looking to enhance your integration skills, or someone seeking to delve into the world of advanced calculus, this video is for you. Let's dive into the world of integration techniques. 1. Integration by substitution. Visual explanation and examples of integration by substitution. Integration by substitution, also known as U-substitution, is a powerful technique used to simplify integrals. We substitute a new variable, u, in place of a complicated expression within the integral. This technique often helps turn complex integrals into simpler ones. 2. Integration by parts. Visual equation for integration by parts and examples. Integration by parts is another valuable technique that deals with products of functions. It's derived from the product rule for differentiation. The formula is u dv equals of v do, where u and dv are chosen parts of the integrand. 3. Trigonometric integrals. Visual, explanation and examples of trigonometric integrals. Trigonometric integrals involve integrating expressions with trigonometric functions like sine, cosine, and tangent. Special trigonometric identities and techniques are used to simplify these integrals. 4. Integration of rational functions. Visual, explanation and examples of integrating rational functions. Rational functions are ratios of polynomials. Integration of rational functions often involves partial fraction decomposition, where you break down a complex fraction into simpler fractions and integrate each separately. 5. Integration of exponential and logarithmic functions. Visual, examples of integrating exponential and logarithmic functions. Integrating exponential and logarithmic functions requires understanding their unique properties. Techniques like exponentials with linear arguments and logarithmic differentiation are helpful in these cases. 6. Trigonometric substitution. Visual, explanation and examples of trigonometric substitution. Trigonometric substitution is used to simplify integrals involving radical expressions. By substituting x with trigonometric functions like sine or tangent, we can transform the integral into a more manageable form. 7. Improper integrals. Visual, explanation and examples of improper integrals. Improper integrals deal with integrands that have infinite limits or infinite discontinuities. We evaluate these integrals by taking limits. They are essential in calculus, particularly when dealing with unbounded regions. 8. Applications of integration techniques. Visual, real-world applications involving integration. Integration techniques are not just mathematical tools, they have numerous practical applications. They are used in physics to calculate quantities like work and center of mass, in engineering for problems involving rates of change, and in economics for analyzing cumulative data. Conclusion. Visual host summarizing key points. In conclusion, mastering a variety of integration techniques is essential for tackling a wide range of integrals in calculus and beyond. Whether you're dealing with substitutions, trigonometric functions, or complex rational expressions, having a toolkit of integration techniques at your disposal will make your journey through calculus smoother. Closing shot of a mathematical integral symbol. If you found this video informative and want to see more math-related content, please give it a thumbs up and consider subscribing to our channel. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching. Your channel name, and happy integrating. Introduction. Opening shot of a mathematical integral symbol. Welcome to your channel name. In this video, we're going to dive into the world of calculus and explore the concept of the definite integral. Whether you're a calculus student looking to deepen your understanding, or someone curious about the power of integration, this video is for you. Let's unravel the mysteries of the definite integral. 1. What is the definite integral? Visual, illustration of a definite integral symbol. The definite integral, often represented by AB, fx, dx, is a mathematical concept that deals with measuring the accumulation, or net area, under a curve between two specific points A and B on the x-axis. It tells us how much stuff is enclosed by the curve within that interval. 2. Notation for the definite integral. Visual, examples of definite integral notation. The notation for the definite integral includes the integral symbol, the function fx, that we want to integrate, and dx indicating the variable with respect to which we're integrating. Additionally, AB specifies the interval over which we're performing the integration. 3. Interpreting the definite integral. Visual, geometric interpretation of the definite integral. Geometrically, the definite integral represents the signed area between the curve y equals fx and the x-axis within the interval AB. It's signed because the area above the x-axis is considered positive, while the area below is considered negative. 4. Finding the definite integral. Visual illustration of finding the definite integral. To calculate the definite integral, we follow these steps. 1. Divide the interval AB into smaller subintervals. 2. Approximate the area under the curve within each subinterval. 3. Sum up these approximations to get an estimate of the total accumulated area. 4. As we make the subintervals smaller and the approximation more precise, we approach the true definite integral value. 5. The fundamental theorem of calculus. Visual, explanation of the fundamental theorem of calculus. The fundamental theorem of calculus is a fundamental concept in calculus that links differentiation and integration. It states that if fx is an antiderivative of fx, if x equals fx, then the definite integral of fx from a to b is equal to fb phi. In other words, it allows us to evaluate definite integrals more efficiently. 6. Properties of the definite integral. Visual, examples of properties of definite integrals. The definite integral has several properties, including linearity, the integral of a constant, and the integral of a sum or difference. Understanding these properties can simplify the evaluation of integrals. 7. Applications of the definite integral. Visual, real-world applications involving definite integrals. The definite integral has numerous practical applications in various fields. It's used in physics to calculate work, in engineering to find the center of mass, and in economics to determine accumulated values like total profit or loss. Conclusion. Visual host summarizing key points. In conclusion, the definite integral is a powerful mathematical tool that allows us to measure accumulation and net area under curves within specific intervals. It has broad applications in mathematics, science, engineering, and beyond. Closing shot of a mathematical integral symbol. If you found this video informative and want to see more math-related content, please give it a thumbs up and consider subscribing to our channel. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and happy integrating. Introduction. Opening shot of a mathematical integral symbol. Welcome to your channel name. In this video, we're diving into the fascinating world of calculus to explore the concept of the indefinite integral. Whether you're a calculus student looking to deepen your understanding, or someone curious about the fundamental principles of integration, this video is for you. Let's uncover the mysteries of the indefinite integral. 1. What is the indefinite integral? Visual, illustration of an integral symbol. The indefinite integral, often denoted by the integral symbol, is a mathematical operation that's all about finding antiderivatives. An antiderivative is essentially the reverse process of differentiation. Instead of finding how something changes over time, we're discovering the original function itself. 2. Notation for the indefinite integral. Visual examples of integral notation. The notation for the indefinite integral is fx dx, where fx represents the function we want to integrate, and dx indicates the variable with respect to which we're integrating. Think of dx as a tiny change in x. 3. Finding antiderivatives. Visual demonstrations of finding antiderivatives. The process of finding an antiderivative involves working backward from a known derivative. If you have a function fx, you can find its antiderivative, often denoted as fx, by asking, what function, when differentiated, gives me fx? 4. The power rule of integration. Visual equations for the power rule of integration. The power rule of integration is a handy tool for finding antiderivatives. If you have fx equals xn, the antiderivative is fx equals xn plus 1 n plus 1 plus c, where n is any real number except -1, and c represents the constant of integration. 5. Rules for indefinite integration. Visual, examples of integration rules. Along with the power rule, there are other rules for integrating different types of functions. These rules include the constant multiple rule, the sum and difference rule, and rules for trigonometric and exponential functions. 6. The constant of integration c. Visual, explanation of the constant of integration. When finding antiderivatives, you'll often notice the plus c at the end of the result. This constant of integration represents all the possible functions that have the same derivative. It's crucial to include c to account for these possibilities. 7. Geometric interpretation. Visual, geometric interpretation of the indefinite integral. Geometrically, the indefinite integral represents the accumulation of an area under a curve. When you integrate fx with respect to x, you're finding the area between the curve and the x-axis over a specified interval. 8. Applications of the indefinite integral. Visual, real-world examples involving indefinite integration. The indefinite integral has various practical applications. It's used in physics to calculate displacement, in economics to determine total revenue, and in engineering to analyze dynamic systems. Understanding integration is essential for solving real-world problems involving rates of change and accumulation. Conclusion. Visual host summarizing key points. To sum it up, the indefinite integral is a powerful tool in calculus that allows us to find antiderivatives and understand how functions accumulate over time. By following integration rules and accounting for the constant of integration, we can unlock the secrets hidden within mathematical functions. Closing shot of a mathematical integral symbol. If you found this video informative and want to see more math-related content, please give it a thumbs up and consider subscribing to our channel. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and happy integrating. End.